Welcome to our deep dive into the fascinating world of isomerism in organic chemistry. Isomerism is a fundamental concept that explains how compounds with the same molecular formula can have different structures and properties. This phenomenon is central to understanding the diversity of organic molecules and their behaviors. Throughout this video, we'll explore the different types of isomerism, their significance, and how they impact the physical and chemical properties of organic compounds. Let's embark on this journey to unravel the secrets behind molecular diversity and see why isomerism is such a crucial topic in organic chemistry. Let's define what isomers are. Isomers are molecules that share the same molecular formula but differ in the arrangement of their atoms. This means that while they have the same number and type of atoms, the way these atoms are connected or oriented in space can vary. This small difference can lead to significant changes in the properties of the compounds. Understanding isomers helps chemists predict reactivity, biological activity, and even the taste or smell of a substance. Let's look closer at the main categories of isomerism and how they are classified. Isomerism in organic chemistry is broadly divided into two main types: structural isomerism and stereoisomerism. Structural isomers differ in the connectivity of their atoms, while stereoisomers have the same connectivity but differ in the spatial arrangement of their atoms. Each of these categories contains several subtypes, each with unique characteristics and implications. By understanding these types, we can better appreciate the complexity and versatility of organic molecules. Let's begin with structural isomerism. Structural isomers, also known as constitutional isomers, have the same molecular formula but their atoms are connected in different ways. This leads to variations in the structure and consequently the properties of the compounds. Structural isomerism itself can be further divided into several types, including chain isomerism, position isomerism, functional group isomerism, and more. Each type highlights a different aspect of how atoms can be rearranged within a molecule. Anisomerism occurs when compounds have the same molecular formula but different arrangements of the carbon skeleton. For example, butane and isobutane both have the formula C4H10, but their carbon atoms are connected differently. This difference in the carbon chain leads to variations in physical properties such as boiling points and melting points. Chain isomerism is common in alkanes and highlights the flexibility of carbon atoms in forming diverse structures. Position isomerism arises when the functional group or substituent is attached to different positions on the same carbon chain. For instance, in the case of butanol, the hydroxyl group can be attached to the first or second carbon atom, resulting in different isomers. This type of isomerism affects the chemical reactivity and physical properties of the compounds. Position isomerism is especially important in understanding the behavior of alcohols, halides, and other functionalized molecules. Functional group isomerism occurs when compounds have the same molecular formula but different functional groups. For example, ethanol and alcohol and dimethyl ether. In ether, both have the formula C2H6O, but their functional groups are different. This leads to completely different chemical and physical properties. Functional group isomerism demonstrates how the arrangement of atoms can transform a molecule's identity and behavior. Metamerism is a type of structural isomerism where compounds have the same molecular formula and functional group, but differ in the nature of the alkyl groups attached to the functional group. This is commonly seen in ethers, where the length of the carbon chains on either side of the oxygen atom can vary. Metamerism highlights the subtle ways in which organic molecules can differ, even when their core functional group remains unchanged. Tautomerism is a special case of isomerism where compounds exist in dynamic equilibrium, rapidly interconverting between two forms. The most common example is Keto-Enol tautomerism, where a hydrogen atom shifts position along with a double bond. This phenomenon is important in many biological and chemical processes, as the two forms often have different reactivity and stability. Tautomerism illustrates the dynamic nature of organic molecules. Chain isomerism occurs when compounds with the same molecular formula can exist either as open-chain acyclic or closed-ring cyclic structures. For example, hexane and cyclohexane both have the formula C6H12, but one is a straight chain and the other forms a ring. This type of isomerism is significant in understanding the diversity of organic compounds and their unique properties. Now let's shift our focus to stereoisomerism. Unlike structural isomers, stereoisomers have the same connectivity of atoms but differ in the spatial arrangement of these atoms. This difference in three-dimensional orientation can have profound effects on the properties and behavior of molecules, especially in biological systems. Stereoisomerism is a key concept in fields like pharmaceuticals, where the 3D arrangement can determine a drug's effectiveness. Symmetric isomerism, also known as Cis-Trans isomerism, is a type of stereoisomerism found in compounds with restricted rotation such as alkenes. In these molecules, the arrangement of groups around a double bond can lead to two distinct forms: cis same side and trans opposite sides. This seemingly small difference can have a big impact on the physical and chemical properties of the compound, including melting and boiling point. Optical isomerism is another important type of stereoisomerism. It occurs when molecules are non-superimposable mirror images of each other, much like your left and right hands. These isomers are called enantiomers. Optical isomerism is especially significant in biology and medicine, as different enantiomers can have drastically different effects in living organisms. The study of optical activity helps chemists understand and control these effects. Chirality is a property of a molecule that makes it non-superimposable on its mirror image. Chiral molecules usually have a carbon atom bonded to four different groups, known as a chiral center. This leads to the existence of two enantiomers, each with unique optical properties. Chirality is a key concept in understanding the behavior of biological molecules, as many biomolecules are chiral and interact differently with each enantiomer. Enantiomers are pairs of molecules that are mirror images of each other but cannot be superimposed. Despite having identical physical properties such as melting and boiling points, they differ in the way they interact with plain polarized light and with other chiral substances. One enantiomer may rotate light to the right dextrorotatory, while the other rotates it to the left levorotatory. This property is crucial in many chemical and biological processes. Diastereomers are stereoisomers that are not mirror images of each other. Unlike enantiomers, diastereomers have different physical and chemical properties. They may differ in melting points, boiling points, and reactivity. Diastereomers often arise when a molecule has two or more chiral centers, leading to multiple possible configurations. Understanding diastereomers is essential for predicting the behavior of complex organic molecules. Isocompounds are a special class of stereoisomers. They contain multiple chiral centers but are superimposable on their mirror images due to an internal plane of symmetry. As a result, mesocompounds are optically inactive even though they have chiral centers. This unique property makes them an interesting exception in the study of stereoisomerism and highlights the importance of symmetry in molecular structures. Racemic mixture contains equal amounts of two enantiomers of a chiral compound. Because the optical activities of the two enantiomers cancel each other out, racemic mixtures are optically inactive. These mixtures are common in chemical synthesis, where both enantiomers are often produced in equal proportions. Separating racemic mixtures into pure enantiomers is a key challenge in pharmaceutical chemistry. Dissolution is the process of separating a racemic mixture into its individual enantiomers. This can be achieved through various methods, such as using chiral reagents, chromatography, or crystallization. The ability to obtain pure enantiomers is crucial in industries like pharmaceuticals, where the biological activity of each enantiomer can differ dramatically. Resolution techniques are a vital part of modern organic chemistry. Isomerism plays a critical role in the pharmaceutical industry. Many drugs exist as enantiomers, and often only one form is therapeutically active, while the other may be inactive or even harmful. Understanding and controlling isomerism ensures the safety and efficacy of medications. This is why regulatory agencies require detailed analysis of isomeric composition in drug development. Isomerism is not just a laboratory curiosity, it's found throughout nature. Many biomolecules such as amino acids and sugars exist as specific isomers. For example, only L-amino acids are used to build proteins in living organisms. The specificity of isomerism in biological systems is a testament to its importance in life processes and evolution. Do you know that isomerism can affect how things smell? For example, the two enantiomers of Carvone smell completely different. One smells like spearmint while the other smells like caraway. This is because our biological receptors can distinguish between different isomers, leading to unique sensory experiences. Isomerism truly shapes our perception of the world. Just like with smell, isomerism can also influence taste. Some isomers of sugars taste sweet while others do not. The arrangement of atoms in a molecule determines how it interacts with taste receptors on our tongues. This is another fascinating example of how subtle changes at the molecular level can have noticeable effects in our daily lives. The action of drugs in the body is often highly dependent on isomerism. For instance, one enantiomer of a drug may be effective in treating a condition, while the other may cause side effects or be inactive. This is why drug manufacturers invest heavily in producing and testing specific isomers to ensure the best therapeutic outcomes. Isomerism also plays a role in food chemistry. The structure of fats, for example, can be either cis or trans, affecting their nutritional value and health effects. Trans fats, which are a type of geometric isomer, have been linked to negative health outcomes, while cis fats are generally considered healthier. Understanding isomerism helps us make better dietary choices. Materials science, isomerism can influence the properties of polymers and other materials. The arrangement of monomer units can lead to different physical characteristics such as strength, flexibility, and melting point. By controlling isomerism, scientists can design materials with specific properties for various applications, from packaging to electronics. Isomerism also has environmental implications. Some isomers of pesticides or pollutants may be more toxic or persistent in the environment than others. Understanding the isomeric composition of these substances helps scientists assess their impact and develop safer alternatives. Isomerism is thus a key consideration in environmental protection and sustainability. In industrial chemistry, isomerism affects the production and properties of chemicals used in manufacturing. For example, different isomers of hydrocarbons can be used as fuels, solvents, or raw materials for plastics. The ability to control and separate isomers is essential for optimizing industrial processes and product quality. Isomerism can even influence energy storage and release. Some isomers store more chemical energy than others, making them useful in fuels and explosives. The study of isomerism helps scientists design safer and more efficient energy sources, contributing to advancements in technology and sustainability. Isomerism remains a vibrant area of research in organic chemistry. Scientists are continually discovering new types of isomers and developing innovative methods to study and manipulate them. Advances in analytical techniques such as spectroscopy and chromatography have made it possible to identify and separate isomers with great precision. Spectroscopy is a powerful tool for analyzing isomers. Techniques such as nuclear magnetic resonance (NMR) and infrared IR spectroscopy allow chemists to distinguish between different isomers based on their unique spectral signatures. This capability is essential for identifying the structure and purity of organic compounds in both research and industry. Chromatography is another essential technique for separating isomers. By exploiting differences in physical or chemical properties, chromatography can isolate individual isomers from complex mixtures. This is particularly important in pharmaceuticals and natural product chemistry, where purity and specificity are critical. Synthesis of specific isomers is a major goal in organic chemistry. Chemists use a variety of strategies, including selective reactions and catalysts, to produce the desired isomer. Achieving high selectivity is crucial for efficiency and minimizing unwanted byproducts. Advances in synthetic methods continue to expand our ability to control isomerism in the laboratory. Isomerism isn't just for scientists, it affects our daily lives in many ways. From the flavors in our food to the effectiveness of medicines, isomerism shapes our experiences and well-being. By understanding this concept, we gain a deeper appreciation for the complexity and beauty of the molecular world around us. Study of isomerism continues to drive innovation in science and technology. From developing new drugs to designing advanced materials, the ability to control and manipulate isomers opens up endless possibilities. As research progresses, we can expect even more exciting discoveries and applications in the future. Despite its importance, studying isomerism comes with challenges. Isomers can be difficult to separate and identify, especially when they have similar properties. Advances in analytical techniques and computational chemistry are helping scientists overcome these obstacles, but there is still much to learn. Looking ahead, the study of isomerism is poised for exciting developments. New technologies such as artificial intelligence and machine learning are being used to predict and design isomers with specific properties. These advances will accelerate discoveries in chemistry, medicine, and materials science. Teaching isomerism is a key part of chemistry education. By learning about isomers, students develop critical thinking skills and a deeper understanding of molecular structure and function. Educational resources and interactive models make it easier to visualize and grasp these complex concepts. Isomerism is a common topic in chemistry exams from high school to university level. Students are often asked to identify, draw, and explain different types of isomers. Mastering this topic is essential for success in organic chemistry courses and for building a strong foundation in the subject. Technology is transforming the study of isomerism. Computer modeling and simulation allow chemists to predict the properties of isomers before they are synthesized. These tools save time and resources, making research more efficient and effective. The integration of technology and chemistry is opening new frontiers in the field. The impact of isomerism extends beyond the laboratory. It influences the development of new products, the safety of medicines, and even the flavors and fragrances we enjoy. By understanding isomerism, society benefits from safer, more effective, and more enjoyable products in everyday life. Let's recap what we've learned about isomerism in organic chemistry. We explored the definitions, types, and significance of isomers, including structural and stereoisomerism. We saw how isomerism affects properties, applications, and even our senses. Understanding isomerism is essential for anyone studying or working in chemistry. We also discussed the wide-ranging applications of isomerism, from pharmaceuticals and food to materials science and environmental chemistry. The ability to identify, separate, and control isomers is a cornerstone of modern science and technology. Isomerism continues to inspire innovation and discovery. As we look to the future, the study of isomerism promises even more exciting breakthroughs. With advances in technology and a deeper understanding of molecular structure, scientists are poised to unlock new possibilities in chemistry and beyond. The journey of discovery in isomerism is far from over. Thank you for joining us on this exploration of isomerism in organic chemistry. We hope you now have a clearer understanding of what isomers are, why they matter, and how they shape the world around us. Keep exploring, stay curious, and remember that even the smallest changes at the molecular level can have a big impact.